Earth, a unique planet, restless and dynamic. Continents shift and clash. Volcanoes erupt. Glaciers grow and recede. Titanic forces that are constantly at work, leaving a trail of geological mysteries behind. This episode travels back in time to investigate the greatest geological mystery of all, the birth of the Earth. Scientists explore how our planet first formed from the dust of the solar system, how molten rock solidified to land, how our oceans filled with water, and how life arrived on Earth. These are the earliest chapters in the incredible story of how the Earth was made. When it comes to finding clues to the birth of the Earth, our planet has been good at covering its tracks. Billions of years of erosion, volcanic activity, and the shifting of continents and oceans have destroyed almost all the evidence of the earliest stages in Earth's formation. For geologists trying to discover how and when the Earth first formed, this is a major challenge.
As geologists began to question the age of the Earth, and of course they looked for older and older rocks, what we began to find was that the further back you go in Earth history, the harder it is to find any of those rocks.
The search for the oldest rocks on Earth brings investigators to the harsh desert landscape of northern Arizona. This giant hole in the ground is Meteor Crater, formed when a massive meteorite slammed into the Earth.
We didn't really have rocks from the very beginning. Well, where could we find something? What about the meteorites that have been out in space and fall on the Earth?
It was here that geologists made a vital discovery. Meteorites are older than any rocks on Earth. They had found the key that would unlock the secret of Earth's formation. If the oldest rocks came from space, that is where the investigation must begin, in space. Our solar system, 4.5 billion years ago. At its center, the young sun.
The theory that emerged was that the sun was surrounded by a cloud of dust and gas, and as that cloud cooled, little grains of minerals formed. So all these little grains of minerals floating in this gaseous cloud are moving around the sun, and they start to bump into each other.
But there was a problem with this theory. Nobody could explain how colliding microscopic mineral grains could ever create an object the size of a planet. Then, in 2003, an experiment on board the International Space Station accidentally provided extraordinary new evidence. Astronaut Don Pettit wanted to see what happened to different substances in the zero-gravity conditions of space. He did a simple experiment by pouring some salt into a plastic bag and shaking it. The results were astounding. The particles immediately began to stick to each other, forming little clumps, all held together by tiny static electric charges. Scientists realized that if grains of salt stuck together in space, then so could the mineral grains in the solar dust cloud. Here was real evidence for the fundamental mechanism that kick-started the formation of the Earth. As mineral grains in the solar dust cloud bumped into each other and stuck together, they grew into small pieces of rock orbiting the sun. Over the next few million years, some of them collided and grew bigger. Many of these rocks are still orbiting the sun today. they have drifted for the past 4.5 billion years, unchanged from when they first formed. Occasionally, they fall to Earth, and we call them meteorites. They provide scientists with an incredible window onto the past.
We brought what's called a stony type of meteorite. What the scientists do then is slice across it and look on the inside. And to a planetary mineralogist, you start seeing all kinds of wonderful things.
This meteorite contains minerals and metals from every part of the solar dust cloud.
So what we're looking at is the assemblage of all these little ancient materials that were floating around the sun in the nebula of dust and gas. And when they hit each other, they gradually aggregated into solid bodies, which got bigger and bigger.
Gradually, billions of these rocks grew as they orbited the sun. First to the size of boulders, then as big as houses, and they kept on growing. When an object reached about half a mile across, its own gravitational pull became strong enough to draw other objects towards it.
Some object in this huge number of objects going around the sun, one of them had to be the biggest. And as soon as it gets bigger than the others, it's sweeping up more objects, just like you're driving through a cloud of mosquitoes at night in your car and the front windshield's getting hit more often. So the bigger it is, the faster it grows. And the faster it grows, the more gravity it gets, and that pulls in more objects. So the biggest object starts to run away from the crowd. It starts to grow fastest.
And that biggest object was the fledgling Earth. Soon, the young planet had so much gravitational pull that it began to attract bigger and bigger objects. As they crashed onto its surface, Earth's size increased with every impact. The bombardment was so intense that it only took about 30 million years for the planet to grow to almost its present size. The young Earth was made of billions of pieces of rock randomly stuck together. But geologists know that the modern Earth is not like that. Below the surface, Earth is separated into distinct layers: a thin crust, then a massive dense layer of rock called the mantle, and at the center, an iron and nickel core. Some extraordinary event must have occurred to transform the interior of the young planet. Geologists now believe that soon after it formed, the Earth completely melted.
Originally, the Earth was probably just a big collection of rocks like this, but it heated up to the point where these rocks all melted. And when that happened, the denser elements sank down through to the very core of the Earth, and the lighter elements floated at the top.
The huge gravitational pull dragged the heavy iron and nickel down to form the core and separated the rest of the planet into layers. What caused such a huge mass of rock and metal to heat up in the freezing depths of space puzzled geologists for many years.
We think it's from the incorporation of very hot radioactive elements. They're out there floating in space. As the Earth accretes, it includes some of this ferociously hot material. As it gets inside there, it begins to heat up the rocks around it. And if you build the Earth fast enough and you incorporate enough of this really hot radioactive elements, it'll be enough to melt the Earth from the inside out.
Only 30 million years after it began to form, Earth had become a giant round ball of boiling liquid rock and metal orbiting the sun.
Imagine a totally molten world. I mean, it had molten magma oceans, no dry land anywhere, no water, just flowing lava everywhere.
The temperature of the molten Earth was now a staggering 2,000 degrees.